And here's some examples from problem set number 4. So with problem set number 4, we're going to be doing a lot of pre-calculus and trigonometry. Yeah, there will be some derivatives, the calculus part, but a lot of it is from trigonometry and pre-calculus. For example, this one right here. I'm not even saying take the derivative, just a review from trigonometry. How do you solve this equation? Well, the first thing to do is divide both sides by 5. So tangent of 2x is 2/5. And now we can use tangent inverse. Oh, by the way, look right here, I graphed it. So I've got one side of the equation is the 5 tangent of 2x, and the other side is 2. And then set up the window to go from 0 to 2 pi so that it covers this. And then take a look at the graph. And where do these two intersect? There's 1, 2, 3, 4. So we're looking for 4 answers. Now when you do the tangent inverse of 2/5, the calculator is only going to give you one answer. And it's going to give you the answer that's closest to the origin. So we get a 0.381. So that means that 2x is equal to a 0.381. Now, as I just showed on the graph, there's actually 4 solutions. What I need to do is set up the 4 equations for those 4 solutions, and then at the end, divide by 2. So that's going to be the very last thing, is divide by 2. So right now, what I do is I look at the tangent function, just regular tangent function. It's got these two asymptotes at negative pi over 2 and positive pi over 2. And then this equation is saying, look at the tangent graph. For the moment, I'm just ignoring the 2x part. Look at the tangent graph. When does it equal 2/5? So here on the y-axis is 2/5. And if you go across, that's going to be the 0.381. Now, what about 3 more solutions? Well, if you draw another branch of the tangent function and continue this line straight across, this would be the second solution. Now, the period of tangent is pi. So to go from this node to this one, you just add pi. So to this 0.381, I'll add pi. Then if you want a third solution, just have another branch of tangent go across. And to go from this node to this node, add on another pi. And if you want another solution, add on another pi. So we're going to have 2x equals the 0.381. And then for this one, it's going to be the 0.381 plus pi, then plus 2 pi, then plus 3 pi. And then divide them all by 2. So my final solutions will go right here after I divide by 2. So I have the original 0.381, and then I could just say divided by 2. So that's going to be a 0.190. Now take the 0.381, add pi, hit enter, divide by 2. 1.761. Take 0.381 plus 2 pi, hit enter, and divide by 2. 3.332. And I could also do it this way, put it in parentheses, add 3 pi, parenthesis, and divide by 2 of 4.903. Now what I'm going to do is check to see if these answers are correct. What I'll do is just randomly pick one, this one. And if that one's correct, most likely I got them all correct. So just go back to the graph, or you could go to trace. This is the second answer, so that should be this one right here. So this one right here should be 1.761. 1.761 should be that point right there. Excellent. So I'm pretty confident that these are correct. Now on to example number 2. Find one value so that the derivative is equal to 0. And to make it even more interesting, have it be one positive. One positive value that makes the derivative equal to 0. And the function for this one is going to be y equals cosine of the square root of x. So you don't have to graph it, but I find that it helps. Let me erase this one, and now the new one is going to be cosine of the square root of x. And from 0 to 2 pi, that sounds fine because those are positive values. Cosine ranges between -1 and 1, so I'm just going to make the y's between -1 and 1. And then look at the graph. Looks like there's no place in here where the derivative equals 0. All of this, the derivative would be negative because it's going down, going down, going down, going down. That's when the derivative is negative. So I should make the window a little bit bigger. How about from 0 to 10? Oh, almost made it. How about from 0 to 20? Okay, so right there, that's where the derivative would equal 0, when it reached that bottom point right there. Now, actually do the calculus. What's the derivative of cosine? So the derivative of cosine is negative sine, and the chain rule says you can only take one derivative at a time, so the square root of x has to stay there for now. Then take the derivative of the square root of x, which is 1 over 2 times the square root of x. So there is the derivative. Now when you set this equal to 0, it's basically a fraction. This is on the top, this is on the bottom. The only way a fraction can equal 0 is if the top equals 0. So really we need negative sine square root of x. When does that equal 0? Or if you multiply both sides by -1, when does sine equal 0? And for the moment, I'm just ignoring the square root of x. It's basically saying if you look at the sine graph, when does the sine graph equal 0? So here's the regular sine graph. This would be 2 pi, this would be pi, and this would be 0. So there's 3 times when the sine function equals 0. But to make it more interesting, I said it needs to be positive. 0 is not a positive number. So the first positive one is going to be pi. So I'm going to use pi, and now go back and use this. So when does the square root of x equal pi? Well, just square both sides, and it's going to be pi squared. Now let me go to the graph and see if that looks correct. So go to trace, and that point right there, it says x equals 10, but that should actually be pi squared. So trace and go to pi squared, and yep. So it was very close to 10, 9.87, but that is where the derivative equals 0. You could also verify by going second calculate, and then derivative, and then plug in the pi squared. And right there, it says the derivative equals 0. So this is correct. Now we're ready for example number 3. So the directions for this one are similar. Find one positive value so that, but this time it's going to be the second derivative equals 0. So the derivative of the derivative. And this function is going to be y equals cosine squared Sometimes I like to graph it first and then do the work. Sometimes I do the work first. Here I'm going to do the work first. So this is the squaring function. To take its derivative, you bring the 2 down in front and then subtract 1 from the exponent. Now do the chain rule. Take the derivative of cosine, which is negative sine of x. Now when I go to do the second derivative, I could do the product rule. But I could also look at this as, let me just put the negative in front, and I'll even put the sign in front. And if you look at this part, there's a trig identity for that. The negative just stays there, and the trig identity for 2 sine of x times cosine of x is sine of 2x. So I didn't have to do this. I could have just taken the derivative of this using the product rule, but it would be easier to simplify it with this little trig identity. Now for the second derivative. So the negative stays there. The derivative of sine is cosine. And then the chain rule. Take the derivative of the inside, which is a 2. And then set this equal to 0. To simplify this, you could divide both sides by 2 or even a negative 2. The left side will still equal 0. And then it's just going to say, when does cosine of 2x equal 0? So again, for the moment, just ignore the 2x part. It's basically saying, when does cosine equal 0? So cosine looks like this from 0 to 2 pi, which means right here in the middle is pi. And right here is pi over 2. So that would mean that 2x is equal to pi over 2. And then divide both sides by 2, and it's going to be pi over 4. So this is for the second derivative equal to 0. So that means that at this point, it's going to be changing concavity. So I haven't graphed it yet, so I don't know exactly what it looks like. But if it's changing from this, which is concave down, to this, which is concave up, then it's this point right here, which is called a point of inflection. That is where the second derivative equals 0. So we should see something like that. Now, graph the original function. Y equals cosine of x being squared. Pi over 4 isn't that big, so I think I'll adjust the window. Go from 0 to pi over 2. That way pi over 4 will be right in the middle. And then, so that part looks like it is concave down. It's not as extreme as mine is, like I wrote over here, but this is concave down and this part is concave up. So if you trace and put pi divided by 4, that'll be right in the middle. So this is concave down and this side is concave up. So pi over 4 is correct. Now, example number 4. So this is going to use implicit differentiation. So again, find one value so that the derivative equals 0. And believe it or not, this one is not going to have trigonometry. We've got e, which is raised to x times y plus y equals x. Now, because this is an implicit function, in other words, I can't just solve for y, that means I'm not going to be able to use this calculator, because when on this calculator, you have to be able to put what y equals. So, gonna have to do it without the calculator. Take the derivative. The derivative of the e function is the e function. Then do the chain rule. Take the derivative of this x times y. That's going to require the product rule. So take the derivative of x, which is 1, and then leave y alone. Plus, leave x alone and take the derivative of y, which is y prime. Plus y prime. And on the right side, the derivative of x equals 1. Now you could do the algebra to solve for y prime and then plug in that y prime equals 0. Or you could plug in the y prime equals 0 right now, right there, and then solve for x. So it'd actually be easier to plug in y prime equals 0 right now, because this will be 0 and this will be 0. So all that's left is the e to the xy, and then this would still be there. So that's just a y. This will be a 0, this will be a 0, and then it equals 1. So, when does this equal 1? Well, I know that e to the 0 equals 1. So if I make x equal to 0, it would look like this. E to the 0 times y equals 1. Well, e to the 0 equals 1, which then means that y equals 1. So my final answer is actually a point, 0, 1. Okay, on to the last one. And the last one, I'm probably not going to do all of the work for it, but I just wanted to show you the last page of this problem set looks like this. So it actually looks exactly like this, except I just changed the function. So what you do is get a piece of scratch paper and first of all, take the derivative. So what you're going to do is do your work on a separate piece of paper and then put your answers here. So for the derivative, well, with this one, I don't actually need to use the scratch paper. The derivative is going to be 3x squared minus 6x minus 24. The critical value, that means set it equal to 0, solve for x. Also find out if there's any place where it's undefined. Since this is a polynomial, there is no place where it's undefined, but there should be two places where it equals 0. And then I could factor out a 3, or I could divide all terms by 3. I'm going to divide all of them by 3. And then I could either factor or use the quadratic formula. I'm going to try factoring. So x and x would make x squared. And then I need two numbers that multiply to be an 8. I'm going to go for 2 and 4. And it needs to be a negative 8. So one of them needs to be positive and one of them needs to be negative. And if you check the middle term, this times this will be negative 4x, and this will be positive 2x, which leaves behind a negative 2x, which is exactly correct. When you set this one equal to 0, it's going to be x equals, oops, forgot my negative, x equals negative 2. And this one will give you x equals 4. So the critical values, x equals negative 2, x equals positive 4. Now, on the one that I gave you, this is a trig function, so it's going to go from 0 to 2 pi. With this, I have negative 2, so I'm going to put that right here on this number line. Here's negative 2, and that's where the derivative equals 0. And then this would be 4, and that's where the derivative equals 0. So what happens on this side? So if you test a number on this side, like negative 3, and then you plug that into the derivative, is it positive or is it negative? Well, let's see. Oh, that glare. Okay, so for the derivative, substitute a negative 3. So 3, and then I'm substituting a negative 3, that gets squared, minus 6 times a negative 3, minus 24. So it's a positive number. The 21 itself isn't all that important. I was just looking to see, is it positive or is it negative? So on this side, the derivative is going to be positive. And that means that the function is increasing. So I can actually start answering this. From negative infinity up to negative 2, the function is increasing. Now pick a number in between negative 2 and positive 4. I'm going to use 0. And if you plug a 0 into the derivative, that's going to be 0 and that's going to be 0. So it's going to equal a negative 24. So that means that it's negative in here. And if the derivative is negative, that means that the function itself is decreasing. So between negative 2 and positive 4, it's decreasing. And then pick a number over here like 5 and plug it into the derivative. So 3 times a 5 gets squared, minus 6 times 5, minus 24. That, oh, what a strange coincidence. That is a positive. So this side is positive. And then that means that it's increasing. So also increasing from 4 to infinity. Okay, now I want to check my work. So I'll graph the original function. So the original was x cubed, and then minus 3x squared minus 24x. And I need the window to go, let's say from negative 5 to, I need to go past 4. I'll go to 8. And for the y values, I don't know what to put, so I'm just going to put negative 10 to 10. And then take a look at the graph. Whoa, it's off the screen. So my guess of negative 10 and 10 wasn't that great. What I'll do is just trace, and right now it's at negative 39. So it's going down to negative 70. Looks like it went to negative 79. So if I go to negative 100 to positive 100, hopefully I can see the graph. All right, that's better. So right here at x equals negative 2, so this is when it's increasing and then decreasing and then increasing. And then that's what this said also. It's increasing and then decreasing and then increasing. So positive means it's going up, negative means it's going down. So it's only the middle part, this middle part, that's going down. And then you could see that this is a maximum value when it got to the top of that hill. So that's negative 2, 28. That is a maximum. Negative 2, 28. And then for the minimum, that would be when I plug in a 4. So that's going to be at 4, negative 80. So with this one, there actually wasn't that much work on the scratch paper, but Go ahead and scan that paper also when you turn this in. Okay, so this one, you basically do the same work except with the second derivative. So the second derivative would be just 6x minus 6. And I know that if x was a 1, this would be 6 minus 6 equals 0. So when this equals 0, that's a possible inflection point. So in other words, x equals 1. So on this, I would just have the number 1 here, and that's where the second derivative equals 0. And then like I did before, you just pick a number on the left and test it. You pick a number on the right and test it. And then finish this just like I did over here. All right, I'll talk to you again soon.